title of my Diagnosing Changes in Earth's Radiation Budget. So first, looking at the relationship between the planet's energy budget and surface temperature, the energy that arrives from the sun really fuels our climate system. So what we're really interested in is how much of that is absorbed. So the absorbed solar radiation is the difference between the incoming solar and the reflected solar. Reflection happens from clouds, from the surface, from molecules in the atmosphere, as well as tiny particles called aerosols. The planet sheds heat by emitting thermal infrared radiation, what I'm calling here outgoing long-wave radiation. The difference between these two is what we call the net radiation. And if you look at a long period of time and there's no external forces acting on the planet, then these two quantities should be the same and the net will be zero. And in that case, since you're not adding or removing heat from the planet, the temperature, the surface temperature, should remain constant. If you now do force, if you add greenhouse gases, or if there's changes in sun or changes in volcanic activity, you do upset the balance. You have a difference. So in the example of where you increase atmospheric gases, what happens is the infrared radiation to space decreases, whereas the absorbed solar radiation doesn't change very much. And so you have a positive imbalance. The net is greater than zero. In effect, you're adding heat to the system. So 93% of this excess energy is stored in the ocean because it's really a good reservoir for heat compared to atmosphere or land or snow. The remainder of the heat that's added goes into warming the atmosphere and land and melting snow and ice. So the bulk of this excess energy goes into energy storage. And so in this case, because you're adding heat, the temperature will increase when you average it over a long period of time. But it's more complicated than that. If you look at timescales of a few decades, there's natural fluctuations in things like the ocean currents and the atmospheric winds that can cause temperature to vary in a way that it could offset or augment the increase in temperature that's associated with global warming. So it's a more complicated system. But what we've observed from CERES since the beginning of CERES is that the planet has been taking up heat. So this is showing the heat content anomaly since the beginning of the CERES period, showing how much energy has been added. And it's showing the yellow is the monthly mean. So you see a sinusoidal pattern there. That's because there's a seasonal cycle to the net radiation. And then the red line is the 12-month running average. So clearly there's been an increase. There's no question that we've been heating the planet based on what we're seeing in the observations. To put this into context, the heat uptake, the rate at which heat is being added, is 344 terawatts. Compare that to the global electricity generation, which is only 5.7 terawatts. So that means the planetary heat uptake is a factor of 60 greater. The other thing we're finding is that there's a trend in this planetary heat uptake, and this is what this is showing. It's showing the net radiation that I talked about earlier as observed by CERES. You see this positive trend. The trend here is 0.42 watts per square meter per decade. That's a large value because if you take 20 years, that's 0.8 watts per square meter. So to compare that, the energy imbalance in this 10-year period was 0.71 watts. So this increase in the rate of heat uptake is not trivial, it's large. So the possible reasons for this positive trend in the net flux, I mentioned the forcings, changes in sun, increasing in greenhouse gases, decreases in aerosol amount. Those are all possible contributors, it turns out that the sun didn't change very much, and aerosols did not have a very large impact. It was mostly the forcing from increasing greenhouse gases that mattered. But there's also feedbacks. Because the temperatures are warming, you can have changes in things like clouds, water vapor, and surface albedo that can exacerbate the initial change in temperature to cause a larger change in the radiative fluxes. So for example, if you increase temperature, you're going to melt snow and ice, and because these are highly reflective, you're going to absorb more radiation. So it's a positive feedback in this case. So at timescales of a few decades, both internal fluctuations and anthropogenic forcing can cause changes in the global net radiation. And so we did an analysis using the observations to try and understand what is driving these increases we're seeing in the net flux. So this is showing the net radiation, the trend, the 0.42 watts. And what it shows is that the combined changes in clouds, sea ice, water vapor, the greenhouse gases, they all exceed the influence from changes in temperature. So temperatures are increasing, so more outgoing radiation is a result, which gives you a negative, contributes a negative trend to net radiation. But the overall effect is that it's positive here because of the sum of all of these positive contributions. We also have an interesting pattern in the net radiation when we look at the regional distribution. You see that over the Eastern Pacific, we're getting these large increases in net. So these are trends, regional trends. And this is mostly because of the low cloud changes. And they are associated with trends in sea surface temperature here, where you have this warming along the Eastern Pacific that really causes a lot of that reduction in cloud cover and increase in net radiation. And this pattern here is very classic pattern. It's a signature of a positive phase of something called the Pacific Decadal Oscillation, which I'll explain here. So the PDO is ENSO-like climate variability, but it happens over much longer time scales, about 20 to 30 years. The warm phase is associated with higher than normal temperatures over the Eastern Pacific, which is shown here, which looks a lot like the slide I just showed in terms of the SSTs. So it turns out that the PDO index, shown in this top plot, went from negative to positive around 2014, given by this dashed line. And when that happened, we saw this big changes in the top of atmosphere radiation. We saw the absorbed solar radiation, the trend in that increased by a factor of 4 compared to prior years. We saw increased emission to space, but it was much more modest in magnitude. And we saw a factor of 2.5 increase in the net flux trend. So while there has been increases in greenhouse gases and feedbacks in response, there's also been these types of changes associated with PDO that contributed to this increase in net radiation. And I just want to show how models compare to finish up. These are the models that are used to project changes in climate as you run different scenarios of greenhouse gases. These are used in the IPCC reports. And what you find is some of the models do very well compared to CERES. CERES is in black, and these are showing the time series of anomalies in net radiation. And you could see this one, for example, is really showing all the same wiggles that we're getting in the observations very nicely. So it gives us confidence that the models are doing the right thing. The physics is okay in these models. So it's a nice, consistent story that we're getting from both observations and models. And I can conclude now. Thank you.